So I'm just going to go through a couple of examples of, like, this is a non-inverting amplifier. Now the key here is I want you to take a good look, because we're going to talk about comparators after, and you might get, when you look at a circuit, you have to be able to determine, is it an amplifier, is it a comparator? Well, the key thing with an amplifier is that the feedback is going back to the negative input. All right? If you see a resistor going from output to negative, it's a pretty good chance it's some kind of amplifier. Now, if there's no feedback, or the feedback goes to the positive input, it's not going to amplify well. You need negative feedback for this thing to work well as an amplifier. Now, remember that this thing here is, this amplifier can pretty much amplify, DC and anything above, maybe up to a megahertz or something like this. So I'm just going to, for this example, I'm going to use a DC voltage, but you could put an AC wave there, you put a sine wave, and it would work exactly the same way. So just for an example's sake here, I'm going to put plus, 1.2 volts. That's for example. The other thing that's going to be a given whenever I give you an op-amp circuit is I'm going to give you the op-amp's open loop gain. So just the op-amp itself, the open loop gain, I'm going to give you that, and we'll say that our open loop gain here for this particular thing is 2 million. So next thing I'm going to do here is I'm going to figure out what the closed loop gain is. So I'm going to say AV closed loop for an amplifier like this. The formula is, because it's an inverting amplifier, minus RF over Rn. And, well, that's going to be 100K, negative 100K over 47K. So take out your calculators and sing along with me. So we'll go 100, we divide by 47, it should be 2 point something. 2.13. There you go. All right, so since I have a voltage at the input, so this is my Vn, I've got a closed loop gain, I can pretty much figure out V out. So V out is going to be my V in times my AV closed loop. So I'm going to take my 1.2 volts, multiply it times my gain of 2.13, and that should give me an output voltage. Let's not forget, this is a negative gain, so there's a phase inversion to make that negative. 2.13. So we'll key in 1.2 times 2.13. Tell me what we have. Negative 2.56. Volts. So at the output, what I'm going to have over here is negative 2.56 volts. Goes in, that's what comes out. Now we're going to take our op-amp theory, and we can figure out a few other things. We can actually figure out what the currents are flowing through these resistors. So first of all, we know that the positive input, we've got 0 volts here because it's grounded. We're calling that 0 volts. And then on the other input, well, see, that's the whole business with the negative feedback. The output is trying to make the other input equal to the positive input. So the op-amp's output is really trying to make this side almost equal this side. This is why we say that the voltage on this particular input, the positive input, is almost 0 volts. That's what the negative feedback is trying to do. It's trying to drive that to almost 0 volts. Almost. We'll find out it isn't exactly 0 volts, but it's very close. Good? Yeah? All So, knowing that, let's take a look at our first resistor, Rin. On one side of the resistor, I've got 1.2 volts. On the other side of the resistor, I've got almost 0. So we could probably safely say that the voltage drop on this resistor, plus 1.2 volts, plus minus, that way. We could probably, safely assume that current is traveling towards the op-amp. So if we know that there's 1.2 volts and there's 47 kiloohms, we can determine the current. That's pretty easy. So In, whatever if you want to call that, you could say, well, that's going to be 1.2 volts divided by 47 kiloohms. That's going to give me a little current. That's your little currents on the island, but it's going to be a small current. little teacher joke there. So, all right, 1.2 divided by 47K. Come on, Kevin, let's go. $25.53 micrograms. 25.53 micrograms. Does everybody concur?
Yeah.
Good. All right, so we know that current is going into there. Now, can any current flow into the inputs as a rule? No. So it's got to go up here. So that means I've got 25.53 microamps that flows into RF, and then that current flows back into the op-amp. So in this case, the op-amp output is not sourcing current, it's sinking it. All right, so the op-amp output is actually taking in current. All right, we know that. So since I've got 25.53 microamps, and let's see here, I can figure out a voltage drop, which is about, well, 2.56 volts, positive, negative. And it makes a lot of sense. Because if you take a look at it, on one side of the resistor, I have almost 0 volts. On the other side of the resistor, I've got negative 2.56. The potential on this side is higher than the potential on this side, so current flows that way. So everything balances itself out. All right? So we know exactly the current, this works out. Everything, voltages are exactly what they should be. Okay, there's one last little thing we might want to determine here, and it's the voltage difference that exists between the two inputs. Well, that voltage difference times the op-amp open loop gain this time is equal to our Vout. We know the open loop gain, I've given you that up here, that's going to be a given on the test. So we know that the open loop gain is 2 million. We know in this case that Vout is negative 2.56. So we can figure out Vdiff. And Vdiff is going to be Vout divided by a open loop. So in this case, it's going to be our negative 2.56 divided by our open loop gain, which we say is 2 million, and is going to give us a very small voltage. You're going to figure that out for me.
$1.28
millivolts. 1.28 microvolts. You sure about that, Kevin?
Well, -6.
Yeah, that's micro. Very good. So what we have at the inputs here, the little difference, so the difference between 0 and almost 0 volts is going to be 1.28 microvolts. And watch this. The polarities are not going to match up with the input, so you're going to have positive up here and negative down here. Okay, see that? Positive and negative, it's the opposite of what the signs are. That's how you get a negative output. Okay? That's why there's negative voltage over there, because if the plus matched up with the plus and the negative with negative, you'd have a positive output. But because they don't, that's got to be the polarity of that little difference right there. Okay? That's that one. So now I'm going to do another one, but I'm going to use a non-inverting amplifier. So I'm going to go over here, and we'll do the same exercise. This time, we're going to do it with a non-inverting amplifier. So again, RF, the feedback resistor, goes back to the negative input. Negative feedback. RN will go to ground. So I'm going to put something like 10K, and I'm going to put 1K here. And I'm going to put an input voltage here. I'm going to put something like, I don't know, 0.8 volts. Positive. I'll tell you that the open loop gain in this case is, for this op amp, 1 million. So we'll start off the same way. We're going to determine, first thing, what's the closed loop gain? So AV closed loop. So for this type of configuration, we know that it is RF over RN plus 1. So we know that that type of configuration, our closed loop gain, is going to be the following. So in this case, we've got 10 divided by 1 plus 1, so our gain should be 11. That should be your closed loop gain. Oh yeah, and the one thing I have to add to both of my amplifiers, and I should, is I'm going to put supply voltage there, so negative 15 and plus 15, so both amplifiers here, we're giving it plus and minus 15 for power. So if I want V out is right over here. Well, V out is going to be, V out is going to be my V in times my AV closed loop. So I've got 0.8 volts times, I just figured out 11. So I guess 8.8. So the output is going to be positive 8.8 volts. Everybody's okay with that? So far, so good? All right. So these are pretty easy. It's just like a little puzzle to solve. That's all it is. Start from one end and go to the other. So, all right. So back to our op-amp theory. If we've got 0.8 volts on this input, well, because of negative feedback, we should have almost 0.8 volts at the other input. That's what the negative feedback is going to try to force that other input as. So we could put a little note here and put, oh, this is about 0.8 volts right there. So far, so good? Yeah. Okay, now watch carefully. On one side of the resistor, I've got 8.8 volts. On the other side, I've got 0.8 volts. That means I've got a voltage drop of 8 volts, positive, negative, like that. Make sense? And on this resistor in the bottom over here, I've got 0.8 from here to ground. So I've got 0.8 volts, positive, negative. On the other resistor, current is, this time the current is coming out of the output. So the current is being sourced by the op amp. So instead of sinking current, we're sourcing current this time. So we could easily find out what that current is. We can take one voltage divided by the resistor. If you take either resistor, doesn't matter, it's got to be the same current. So if you take 8 volts divided by 10K, there's your current. Do that for me. So right over here we can say, well, this is 8 volts divided by 10 kilo ohms. That's the current in RF.
$8
8 milliamps. So you have 80 milliamps flowing out of the output, going through RF, and then through the 1K to ground. Everything good? Oh, 800 microamps. Who gave me that fictitious number? Oh, yeah, yeah. All right, 800 microamps. I stand corrected. Okay, there's only one thing left to figure out, and what's that little voltage difference right at the inputs? So what's the little voltage difference? VDIF. This is where you use the open loop gain. So you'll say VDIF is going to be V out divided by A open loop. So V out is 8.8 volts divided by 1 million. So 8.8 microvolts. And when we put this in, we go over here, 8.8 microvolts. And the polarity, because we've got a positive voltage, matches up with the inputs, plus, negative. And there you go. Now these would be kind of questions I'd put on the test. Maybe one of each of those in a comparator. And if you can figure this out, well, you pretty much aren't going to have any problems with the test. That's just basic op-amp theory.
Is this test open book also?
Yes, it'll be open book. Okay? Now there's another model of amplifier I want to show you. I have to talk about it before we move on to comparators because it's pretty important. You guys are going to study a little bit of instrumentation. So you should know a little bit about instrumentation amplifiers because they're quite common and they're quite handy. And I'll draw one up for you. We can analyze it just like we did this. And I'll explain to you why they use them, why they're so useful. And we'll talk about something called common mode rejection ratio. Get this out. So there are different ways of making amplifiers. So there's one here, we'll call it a differential amplifier. So differential amplifier. And looks like this. And always negative feedback, so we have a resistor going from output to the, so we know it's a pretty good idea, pretty good clue, it's an amplifier. And then I'm gonna have another missile fit. So I'll call this RF1, and I'll call this RN1. And right over here, I'm gonna put another is this? We're going to call this R in 2 and RF2. I'll do that. This will be out. So in this configuration, we're going to apply, we could apply a voltage at both inputs. There's two VINs. There's VIN1 and VIN2. So the other amplifiers we're kind of using in single-ended input, just one input. In this thing, we're going to use differential inputs. We'll use two inputs. And the reason we kind of like this thing, well, here's where we use it. Let's say you're doing some instrumentation. So you got a sensor somewhere in the plant. You're working in some, I don't know, cookie factory or something. I don't know where you're working, but you got a sensor. Now a sensor could be measuring anything. It could be measuring temperature, measuring flow, it could be measuring pressure, who knows. Now the sensor is located far away, so I'm just going to put a sensor here, a little sensor, whatever. It outputs a voltage, and there's these wires, so there's going to be this other wire here. So it's kind of hooked up in this fashion where you've got, plus and negative, and these two wires come all the way. This is called this is kind of what they call a balanced mode. So there's signal on both wires, push and pull type of thing. Now, one of the problems with working in an industrial setting is there's a lot of radio frequency interference going on. There's a lot of electrical energy in the air, all kinds of frequencies. So what often happens is you're going to get 60 hertz, or it could be 400 hertz off a motor or switch. It could be anything. A lot of noise. So that noise, I'm going to put 60 hertz here. So a couple of 60 hertz. So that noise hops onto your wires. So you've got this, thousands of feet of wire going to the sensor. And it's picking up noise. The nice thing about it, the noise is being picked up on both wires. Okay? So when it gets over here, not only do you have the plus or minus voltage from the sensor, but you've also got 60 hertz that arrives with it. 60 hertz here. Which is not so desirable. And in some cases, there could be more noise than there is signal. That's not good. Now, here's the beauty of this little beast, this little op amp, why they built these things, is that it's made to amplify differences, okay? If it gets the same thing on its inputs, it won't amplify it. It cancels it out. So the whole idea with our differential amplifier is that the beauty of this thing is when it sees the same kind of noise on both lines, it rejects it and will only amplify the differences. Okay? So a differential amplifier, what's nice about it, it'll take the voltage that's coming off the sensor, but whatever noise that's hopped on, that is common on both wires, gets canceled out. So there's a specification, when you're looking at a spec sheet from an op amp, there's a particular specification called the common mode rejection ratio, CMRR. I'll write that down. That's common mode rejection ratio. A little number. Now I could go through a whole type of, a whole discussion on how they come up with that. It's usually, it's measured as, voltage gain differential, so AV diff over AV common. There's a method to measuring all that. It's not something for electricians, it's not terribly important. You should just know what the number means. So let me go through a little scale here. So minus 70 dB. So if you're looking at an op amp, the common thing these days, minus 70 70 dB, that's kind of, you should expect that. And that's okay. All right? Now, if you get to something like minus 80 dB, that's good. If you get something like minus 90 dB, that's very good. If you get something that's greater than, well, I should say smaller than, let's say absolute value here, then 100 dB, that's excellent. So when you're looking at amplifiers and you look at that number, that common mode rejection ratio, just remember 70 dB is kind of like run of the mill. Yeah.
What does it say on the bottom? AB diff over?
Oh, that's differential over AV common mode.
Oh.
That's don't worry too much about that. It's not something I'm going to make you calculate. I just want you to know what it means. And what it is, this number is a measurement of how well an op-amp will reject common signals. The truth is that an ideal op-amp will reject it totally. Okay, ideal. But a real life op-amp, if you had exactly the same amount of 60 hertz on both sides, a tiny, tiny wee bit is going to leak through, but very little. And the smaller this number, okay, the better it is at rejecting common noise. So if you're looking at any kind of amplifier, one thing, and it's got differential, one thing you might want to look at is like, what does it say for common mode rejection ratio? And the bigger this number is, going towards negatives, I should say smaller, the better it is. Like again, minus 70 dB, that's to be expected. That's, that's normal. Okay, that's your cheap stuff. But as you get down here, this is where you start paying your money. It gives you excellent rejection. Okay? All right. Now, let's take our amplifier, go back to our amplifier, and I'm going to draw one up over here, just like that. We'll just do a little analysis of it. One will be out, and I'll show you how to figure these out. It's very simple. So let's give these things values 10K, 10K. I'm going to put 10 volts over here, and I'm going to put 2 volts positive plus 2 over here. This will be 10K as well. This will be 10K as well. And I have to put plus over here. All right. So again, like I said, we've got negative feedback, and that's the output trying to make the negative input the same voltage as the positive input. So let's go to the positive input and see what the reference voltage is. So this thing right here, going into here, we can think of as V reference. Here we go. So look carefully. I've got 2 resistors here, 10 volts at the top, ground over here. Hey, this thing is a voltage divider because we have no current going into the amplifier. We know that. So if I have 10 volts, 10K and 10K, it would only make sense if the voltage right at this input from here to ground would be 5 volts. 2 10K resistors, split up the voltage equally. There you go. So that's the reference voltage on one side. So you kind of solve this. This is just a simple voltage divider. And what's the output of the amplifier trying to do to the inverting input? It's trying to make it the same. So we could go over here and say on the other side, this is almost 5 volts as well. This is working out very well now. So, if I have 5 volts on this side and 2 volts on that side, that means I have a voltage drop of 3 volts, plus or minus like that, on that top 10K resistor, right? If 5 volts on this side, you get 2 volts on here, well, you've obviously dropped 3 volts. So you take your 3 volts, you divide by 10K, and tell me what you get. 3.3 something, or 33, whatever. So 330 microamps? 300 microamps? What does everybody else get? It's not going to be 3 because that would make it 9. Okay? 300 microamps. And which way is the current traveling? That way? Well, the voltage potential is higher on this side than it is on that side. It's not sand in here. It's not traveling upstream to meet or anything like that. It's going this way, right? So that means the current up here has got to be doing the same thing. It's got to be coming out of the output. And it's got to be the same amount of current. 300 microamps or so. Right? So if we've got 300 microamps down here, it's got to come from somewhere. It's got to come from up here. So we have 300 microamps that flows through the feedback resistor, comes down here, and then flows to the 10K, and out it goes. Right? So if I had 3 volts on this resistor, well, I should have a 3 volt voltage drop on this resistor because it's the same resistor with the same amount of current. Right? So watch this. If I have 5 volts over here, and I go up by another 3 volts, that means the output has got to be 8 volts. Just take 8, you lose 3, you're down to 5. So in this case, the output would be 8 volts. And if you take a look, our amplifier, 10K and 10K, had a gain of 1, and the difference between the 2 inputs was 8 volts. And the positive side was bigger, so we've got 8 volts at the output, positive. Works like a charm. Is that right? That's a differential amplifier. So you can put 2 voltages into this thing, and it gets amplified, out it goes. It works the same way as everything else. The trick is calculate this reference voltage, and then you know what the voltage is on the other side. All right, so that's our little thing on amplifiers. Okay?